Okay, so I want to introduce a little bit of where we're going for this week. So we're going to start what are called optimization problems. As a warning, these are going to feel maybe a little bit like related rates, in that there's going to be a lot of necessary steps that you have to take, and it might not be the easiest ones, but hopefully once you get the hang of it, then you'll feel really good and you'll feel hopefully very empowered with everything that's kind of coming together as we're applying derivatives. So I want to walk through a few steps, just kind of outline how we're going to do this. There'll be some other videos that I'll have posted where I'll be working through examples so you can see how all of these steps come together for specific cases. Okay, so optimization problems. The goal of an optimization problem is we're going to try to figure out what is the optimal something. So either we're going to try to maximize something or we're going to try to minimize something. So maybe it might be profits, maybe it might be area, maybe it might be perimeter. We're going to be trying to figure out what the question's asking us to do and use our abilities of finding maximums and minimums to figure how this applies in some context. Okay, so the very first step that we want to do when we solve an optimization problem is we want to draw a picture and label variables. So again, similar to related rates, we want to make sure that we're able to visualize what is taking place here. So again, we're going to have a lot of basic shapes of, be it, cubes, rectangles, circles, triangles, cones, those types of things. So start out the same way, draw a picture, label some variables. The next step that we're going to need is we're going to need to create necessary equations or functions. Now, this is going to be where it's going to deviate a little bit from the related rates section, in that there's going to be these two major types of equations or functions that might appear. At least one of them will always, the second one may or may not. So this one, so we need to have a function that we're going to try to maximize or minimize. So if we're asked to find the maximum area of a rectangle, well then you need to have the area of a rectangle. If you're going to try to minimize the volume of a cone, you need to have the equation for the volume of a cone, those types of things. And then there's going to be a constraint, potentially. Most questions will have some constraints, something that's going to be saying, I can't allow myself to have all possible values. There's something that I'm restricted to abide by. So an example might be, how do you maximize the volume of a cone if you're restricted by only having so much amount of material? So that would be something, the constraint would be some type of surface area. That's the material is going to form the cone. Well, do we want to have a really short, skinny cone? Or sorry, do we want to have a tall, skinny cone, or do we want to have a short, fat, wide cone? Which one's going to be able to maximize or minimize volume given the restriction on the surface area? So those would be different equations that we'd want to come up with. The next step we want to do is we want to try to get the function we're maximizing or minimizing in terms of one variable. So this is one that is a major difference between how we approach related rates. In that related rates, we had all types of variables present, and then we did implicit differentiation. We're not doing that. We're trying to get a single equation, a single function in terms of one variable. We saw it a little bit in related rates, but this is going to appear a lot more as an important thing. So we're just trying to figure out what is one function in terms of, say, x. Now, the way that we're going to do this is that's where the constraint, if we have a constraint, that's going to help us. That's going to be able to say, I can write one of the extra variables in terms of the other one. So you'll see that in some examples of how we're going to use that constraint to be able to write the function we're maximizing or minimizing in terms of just one variable. The next step that we'd like to do is we're going to create a feasible region. Now, this is, again, only if possible. So when it comes to these questions, there's going to be a real-world context that we can't just leave all reality behind. So, for instance, if you're asked to maximize area, for instance, if you're looking at the area of a rectangle, you know that the sides of a rectangle cannot be negative. Okay, so that's going to be some type of restriction that we can have on what type of possible, say, lengths we could have, is that they have to be at least positive, and then maybe if we have other constraints that will help us dictate what a different type of bound would be. So we create this feasible region of the possible values that our variable can take that we've solved for. Then the last step that we're going to try to do is we're going to find the absolute maximum or the absolute minimum of the function in the feasible region. And so this is going to look exactly like what we did earlier with derivatives, is you're going to be looking for how do you find the absolute max or the absolute min. Now, we did this always in the context of having a closed region, right? So we would always have endpoints that we would include, and we would always include critical values within that region. Now, that's the nicest way. So that's where the feasible region is very useful, that if we can have our feasible region be a closed interval that has both endpoints, then we simply, to do this, we find all the critical values in the region, and then we find all of the endpoints, we figure out where the function's largest and smallest, and then whatever we're trying to do, maximize or minimize, you pick the biggest or you pick the smallest. Okay, so that is going to be the easiest, kind of most straightforward way. But there's a slight twist that I want to introduce now, is that what if we don't have a closed interval? Because we only talked about finding absolute max and absolute mins when we had endpoints. What happens if we don't have endpoints? So there's this really nice theorem that you're going to want to have available. So if f is defined on an open interval, so that means that there's no endpoints. On either direction, you have no endpoints. Then, if our function has only one critical point, okay, so we have to make these two assumptions. One is that there's no endpoints, and there's only a single critical point. Then, if this critical point is a local maximum, then that actually is an absolute maximum. If it's an absolute minimum, then that's actually an absolute minimum. So we have this nice relationship that if we can show things are absolute max and mins, then we can show they're absolute max and mins if we only have one critical point or one critical value on this open interval. So remember, just as a reminder, when we find things that are local maximums, local minimums, those are going to be using techniques like, say, the first derivative test, where we're going to see where is our function increasing and then decreasing. At any point where our function is defined that changes from increasing to decreasing, which you use the first derivative to tell you that, that's going to correspond to an absolute maximum. Any place where our function goes from decreasing to increasing, and that point is still well defined, then that's going to be a local or relative minimum. So we know how to find these. This allows us to turn the locals into absolutes, or the relatives into absolutes. Now, to help us build a little bit of intuition behind this, the idea is that, so if you have this function that seems to be going up and up and up, for instance, and then it goes down, but let's say this is not the absolute maximum. Okay, so let's say we have ourselves a local maximum, but it's not the absolute maximum. Notice the only way for this to happen is if we had to create another critical point, right? So if this is the only critical point, I'm not allowed to be undefined on that region. And I guess we're assuming also, by the way, that this is a continuous function, by the way. Most of these will be continuous on the intervals we're looking at. But so if we have this, the only way for this local maximum to not be an absolute maximum is if I somehow am going to jump up here and start someplace new, or I'm going to have to form a new critical value. The same thing happens that if I have a local minimum, the only way for this to not be the absolute minimum is if I have to go down below it, but then again, I create a new critical value, but I'm only assuming in this case I have a single one, so this local minimum will end up being the absolute minimum. So again, there'll be some videos that I'm going to work through to help you see some of the examples of how do you work through all of these steps, and whether or not we need to use this theorem. There'll only be a few times. This feasible region is going to be our go-to strategy, that if we can create clear and restricted endpoints on this, it's going to be very easy to be able to find the absolute max and absolute min, because you just check critical values and endpoints.